Hello everyone. In this third video, we're going to cover the last two rules of the basic rules of differentiation. We're going to do rules 9 and 10 involving the natural logarithmic function. But before we do that, I want to give you a warning, okay, concerning rules number 2 and rule 7. Okay, we covered rule 2 in the first video and rule 7 in the last video. Okay, there is a big difference between the functions f of x equals x cubed and g of x equals 3 to the x. You notice that in the function g of x, okay, the 3 and the x are reversed from the function in f of x. So f of x equal to x cubed, that's an example of a power function, okay? And g of x equal to 3 to the x power is an example of an exponential function, okay? So this is an exponential function, this is a power function, okay? Based upon where the x is and where the 3 is. And since these are two vastly different functions, they have two vastly different derivatives. The derivative of f of x equals x cubed by the power rule, right, is equal to 3x squared. In differentiating x cubed, you bring the 3 down in front of the x and subtract 1 from the exponent and you get 3x squared, okay, by rule number 2, basic rule number 2. In differentiating the exponential function with a base of 3, right, that derivative, g prime of x, is equal to the natural log of 3 times 3 to the x by rule number 7. So when you're differentiating, right, and you get these different functions like say on your exam, right, you gotta know there's a big difference between x cubed and 3 to the x. Which rule you use, right, depends upon the type of function you're differentiating, okay? So I just wanted to let you know, okay, warn you, okay, that these are two vastly different functions, and so they have two vastly different derivatives. Now, we're going to talk about the derivative of the natural log function, and I think a lot of students don't really know what that is, where that came from, so I'm just give you a brief overview where the natural log function came from, right? This ln stuff. All right, so you already know about the natural exponential function, right? So I have the equation y equals e to the x. And the graph of the natural exponential function in the coordinate plane looks something like this. It's upward sloping everywhere, right? Going from right to left. And so this is what the graph of y equals e to the x looks like, okay? And it crosses the y-axis here at y equals 1, okay? The entire graph lies above the x-axis. Any number you put in for x up here, right, e raised to that number is a positive number, okay? Well, you know that this graph meets the definition of a function because no matter from your high school algebra, no matter where I draw a vertical line, it intersects the graph in only one location. Well, so this is the graph of a function, but it's also the graph of a one-to-one function. And one-to-one functions have the characteristic that no matter where you draw a horizontal line, it intersects the graph at only one location, or at max one location. So it has an inverse function. Well, what's its inverse function? Well, you can't solve for the inverse function algebraically like we can with many other functions, okay? So mathematicians sort of had to make one up way back when. And what they came up with was the natural log function. And the natural log function has a graph that looks like this. And it crosses the x-axis at x equals 1. So this is the graph of y equals the natural log of x. And since e to the x and the natural log of x are inverse functions of each other, okay, they undo each other in the composite of the two functions. If using your calculator, if you type in the natural log of e to the 5th power, you'll find that the answer to that is equal to 5. The natural log and the natural exponential function, they cancel. We can think of it as they canceled each other. And it's also true that if I take, using your calculator, take the number e and you raise it to the natural log of 5, you get 5. Okay? So the natural log function and the natural exponential function are inverse functions of each other, and they undo each other in the composite. Okay? So it is an important function, the natural log function. Okay? So we're going to learn how to differentiate, right, the natural log function in this video. So rule number 9 deals with the derivative of the natural logarithmic function. Okay? So if I have the function h of x is equal to the natural log of x, right? You can read this as the natural log of x or ln of x. Okay? Then the derivative of h of x, denoted with h prime of x, is equal to the derivative of the natural log of x, which is just 1 over x. Okay. Now I should add a couple of comments here. X, whenever you take the natural log of a number, it has to be greater than 0. It has to be positive. So we should have the restriction that the x that we're taking the natural log of has to be a positive number, right? Greater than 0. Now some people, when they write this on the right hand side, they'll put the x in parentheses. That's okay. You can do that. I put stuff in parentheses in order to clarify things. I don't think it needs to be clarified at this stage. Okay. So if x is greater than 0 and h of x is equal to the natural log of x, then the derivative of h of x, denoted h prime of x, is equal to the derivative of the natural log of x, which is just 1 over x. It's a very straightforward derivative. So in your first example, now I'm on page 20 of your packet, your note packet, we have y is equal to the natural log of x plus x minus the natural log of 4. Now, so we have a function with 3 terms in it, right? ln of x, natural log of x, is the first term, plus x is the second term, minus the natural log of 4 is the third term. And so we know from previous rules, the sum and difference rule, that we can, finding the derivative of this function, we can differentiate each of these terms. We can differentiate the right-hand side term by term. Okay? Now, this last term, the natural log of 4, you don't see an x in that term, do you? So that's actually a constant. Okay? So the natural log of 4, I'm doing this off of the top of my head. I know the natural log of 2 is around 0.69 something. And so the natural log of 4 is going to be twice that amount. So it's roughly around 1.38 something, I think. Okay. So this natural log of 4 is really a constant. okay? And we know the derivative of constant is 0. So the derivative of this function, which we denote with y prime on the left, is equal to the derivative of the natural log of x, which we know is 1 over x, plus the derivative of just x, which we know is 1, and the derivative of minus log 4, that's minus log 4 is equal to minus 1.38, right? That's a constant, and the derivative of a constant is 0. So the derivative of this function, y prime, remember this is a prime, the derivative of this function, y prime, is just equal to 1 over x plus 1. In the second example, we have g of x is equal to the natural log of x plus 1 over x. Well, in finding, so we have a sum of two terms, right? Natural log of x is the first term and 1 over x is the second term, so we can differentiate term by term. We know how to find the derivative of natural log of x from up here, but to find the derivative of 1 over x, we have to change that, right? We have to rewrite that. And so we're going to rewrite this as the natural log of x plus 1 over x is the same as x raised to the minus 1 power, right? Remember, the minus sign in the exponent means reciprocal, so x to the minus 1 is the same as 1 over x to the first power. And there's an invisible 1 in the exponent on the x here, okay? So g of x is equal to the natural log of x plus x to the minus 1. Well, differentiating term by term, we get the derivative of g of x, denoted g prime of x. The derivative of the natural log of x from up here is 1 over x. And then in finding the derivative of x to the minus 1, we use the power rule, right? Rule number 2, basic rule number 2. Bring the minus 1 down in front of the x, subtract 1 from the exponent. So when we bring the minus 1 down in front of the x, instead of plus x, we have minus x, right? There's an invisible minus 1 in front of the x. And then when we subtract 1 from the exponent, we have minus 2. So g prime of x, the derivative of g of x, is equal to the derivative of the right-hand side, which is equal to the derivative of the right-hand side is 1 over x minus x to the minus 2 power. Okay? And so that's the derivative of the natural logarithmic function, okay, in its basic form. Rule number 10 has to deal with the chain rule involving the natural logarithmic function. So let's talk about the chain rule involving the natural logarithmic function. And what we're talking about, instead of x being here inside of the natural log of x, we're replacing x with an algebraic expression. And so when x is replaced with an algebraic expression involving x, you might think that the derivative is going to be just 1 over that algebraic expression, but like with all chain rules, we have that additional step, okay, involving multiplication. So I'm going to leave rule 9 up here. If h of x is equal to the natural log of x, where x is greater than 0, then h prime of x is equal to 1 over x. Now rule 10, as I already said, complicates the situation. Right? We're dealing with the chain rule. For the derivative of the natural logarithmic function. So now instead of x inside the natural log of x, we have a function of x. So I'm going to write if h of x is equal to the natural log of f of x. Okay? So to give you an example, okay, of what we're talking about, is the first example down below. We're going to have the function y equals the natural log of x cubed minus 6x squared plus 3 times pi, right? So the x up here is being replaced with this algebraic expression. Okay? And so when we differentiate, it's not going to be just 1 over this quantity in parentheses. There's going to be one additional step, as in other chain rules. So if h of x is the natural log of some expression, algebraic expression involving x, right? F of x. And we have the condition, right, that f of x has to be positive for all values of x, right? This function has to be positive for all values of x, because you can't take the log of 0 or a negative number. If h of x is equal to the natural log of f of x, then the derivative of h of x, denoted h prime of x, is equal to, up here we did 1 over x, so now we're going to do 1 over f of x. But then we have to multiply that by the derivative of this function inside the natural log. And the derivative f of x we denote with f prime of x. And 1 over f of x times f prime of x can be written as the fraction f prime of x over f of x. So when you differentiate the natural log of a function of x, it's equal to the fraction f prime of x over f of x. So let's work this example right here from your notes. We have y is equal to the natural log of x cubed minus 6x squared plus 3 times pi. Well, you know 3 times pi is equal to 3.141, so 3 times that is just a constant, right? There's no x in that term, okay? So the derivative of this function, y prime, from over here, the first thing you do is you take what's inside the log and you put it in the denominator. So what's inside the log? X cubed minus 6x squared plus 3 times pi. And then you multiply, and then you put in the numerator the derivative of this denominator, right? What's inside the log here, inside parentheses here. And so it's 3 terms. So we differentiate term by term. The derivative of x cubed is 3x squared. The derivative of minus 6x squared is minus 12x. And then the derivative 3 times pi, which, you know, 3 times pi is just a constant, it's around 10. That's equal to 0. And so this is the answer. For this function, y equals the natural log of x cubed minus 6x squared plus 3 pi, the derivative, y prime, is equal to 3x squared minus 12x over x cubed minus 6x squared plus 3 pi. Okay? All right. In the next example, we have h of x is equal to the natural log of 3x to the 5th minus 3x to the 4th minus the natural log of 3. And so again, inside the parentheses here, right, we have 3 terms, and the third term is the natural log of 3. There's no x involved in that term. So this is just a constant. If you type ln of 3, natural log of 3, into your calculator and hit enter, you'll get a real number, a decimal for that value. So the derivative of h of x, which we denote with h prime of x, you put what's inside parentheses in the denominator first. And then you put in the numerator the derivative of what's in the denominator or inside this parentheses. And the derivative of 3x to the 5th is 15x to the 4th. And the derivative minus 3x to the 4th is minus 12x cubed. So that is the derivative of h of x equal to the natural log of 3x to the 5th minus 3x to the 4th minus the natural log of 3. Okay? And so I didn't do it on the previous example, but let me write it on this example. Okay? This in the numerator, okay, writing it in red, is the derivative of what's inside the parentheses. 3x to the 5th minus 3x to the 4th minus the natural log of 3. Okay? So you put what's inside parentheses in the denominator, and then you put in the numerator the derivative of what's inside the parentheses. Okay? And you're done. You've successfully found the derivative. So class, that wraps up the last 2 basic rules of differentiation, basic rules 9 and 10. Okay? And the next video will contain the product rule.